So next speaker is Joseph Leines. Joseph, can you share your screen?
Yes, we'll do it.
Yeah, he's a petroleum and software engineer at Simtech. He developed algorithm code for Simtech core applications in both conventional and unconventional reservoirs. His research area include integrated hydraulic fracture and discrete fracture network software development, Vugs modeling in carbonate reservoir, data-driven modeling, and high performance computing. He holds a bachelor degree in petroleum engineering from University Central de Ecuador and a master degree in engineering from UT Austin. So Joseph, it's all yours.
All right, thank you so much for that introduction. I'm really happy to be here today in front of you guys, at least virtually, and let's start. So this is a talk for EDFM for fractures, Vugs, and Karst systems. So let's start with the outline. I'm gonna talk a little bit about the introduction of carbonate reservoirs, some of the main challenges that we encounter in fracture, Vugs, and Karst systems. Then I'm gonna talk about the current flow models that one can find in the literature. And then also I'm gonna move on to the syntax objective about how to tackle these challenges. I'm gonna talk also about our current approach regarding the preprocessor development and the free flow modeling. And then I'm gonna wrap up the talk with a brief summary. So to start off, let me show you, and let's discuss about this also, how carbonate reservoirs are significant. Basically, we can just look at the numbers. 50% of the proven recoverable reserves are coming actually from the carbonate reservoirs, and the current global production is more than 60%. So around these carbonate reservoirs around the world, we have the fractured bogey carbonate reservoirs, which actually constitute a significant proportion. And we also have some of the most important reservoirs here depicted in this plot. Let me also start recording my talk for the people from Teams that didn't have the chance to do it, but yes, now it looks like it's recording. Sorry for that. Okay, now we can continue. All right. Yeah, so here we can see the most important ones, like in Brazil, Mexico, the Dahim Basin, and China, some in Russia, and in the Middle East as well. So here in this slide, I'm showing you a brief introduction for all the complexities that we have, starting off with the no matrix characterization that Dr. Charlie basically explained thoroughly how challenging it could be to characterize the no matrix. Also, we have challenges regarding the porous flow region and the free flow region modeling. These constitutes an important modeling part that determines the actual free flow in those reservoirs. We also have some interfacial conditions happening in the intersection between both regions that need to be accounted for mathematically. We also have some gravitational effects that may happen and are subject to the Vugs and Karst scale effects. So some of them may be, as Dr. Charles showed, ranging from centimeters, but other ones to dozens of meters. And another challenge that we can find here is the actual representation of the matrix and no matrix interactions. So here is just a brief demonstration of how difficult this could be. So one of the main jobs of geologists is actually determining the pore volume associated to the Vugs and Karst. And for that objective, what they do is to basically gather sources information from all sources of that could be available, ranging from seismic cores, those circulation reports, and to dynamic data. So after integrating all this information, we also, with expertise of the geologist team, they can come up with sound geological models that can
Joseph,
explain. Yes?
Excuse me, because people in Teams, he cannot hear your voice. Maybe you can.
Oh, okay. Yeah, I can try it again. Let me see.
Very sorry. Excuse me, because actually the audience is joining us both through Zoom and from Team. So we have Joseph is working on operate this channel. So we needed to make sure Teams the audience can also heard about his talk.
Can you people from Teams now hear me? Maybe they can. I think now.
Maybe they can. Can you confirm?
Yes. Let me try to see. I think that they can now. Maybe in the chat, can you say? Okay, let me see now. Maybe now.
I haven't gotten any response from the audience yet, but
okay.
Yeah, let's wait a little bit. Or you can continue. So I'll wait for the answer. Still not.
It should be now.
Still not.
But it's not. Wait, let me try to reshare my screen.
Okay.
Okay, now I think that now they'll be able to hear. But yeah, sorry for that inconvenience. Let's continue with the presentation. So we were discussing about how the complexities of the modeling and characterization, and after figuring out all the sources of information, integration of all of them, they can determine or develop or create certain models that can actually depict the reality or as closer as they can. Now let's continue with this other topic that is important. The thing is that even though the model is as accurate as possible, the sad part about this is that their applicability is highly reduced because of the inappropriate fluid flow models that current reservoir simulators have.
Sorry to interrupt again, but they still have problem. Can you check that again?
Yeah.
Or Dr. Miao, do you have Joseph's presentation? So you might want to share the presentation.
Sure. So later on, we will share the presentation and the video, recording.
Okay.
Okay, thank you. Okay, please go ahead.
Yeah, so, okay, let's continue. Sorry for those inconveniences. So as I said, the applicability is highly reduced because of the inability of reservoir simulators to handle free flow. Now let's move on to the other challenges that we have, porous flow region and free flow region. So here in this plot, we can see that the porous system and the fracture system is kind of combined in this way, and because the flow motion will be governed by Darcy's law. But now let's talk about the free flow region per se. So this region basically encompasses some empty cavities with complex geometries and sizes. Here we have some important physics going on, as I said, gravitational effects, a different velocity profile from the actual comparison with the porous region, some slip effects and interfacial conditions as well. So here, because we're talking about an empty cavity, the physical meaning of permeability actually breaks down. And the fluid flow velocity in these flow regions cannot just be assumed as a linear function of pressure gradient. Because of all the physics present here and because some interactions of implications with inertial forces that happens inside of them. Here in this slide, I'm showing you in a little bit more detail about the interface. So here we have a free flow region and a porous media, and we can see here the interface that unites them. Here we have some shear effects that change the velocity from the porous media, the main velocity that we have here. And we see because of these shear effects, we're going to have a transition here that needs to be mathematically described if one wants to model incouplable flows. But that's not the only problem. The other problem is the complexity that this interface shows. Here we can see a simplification of them. But in reality, this complex interface can have a topology that might pose a lot of challenges to represent in 3D when wants to try to model it in a computer. Now let's talk about the gravitational effects. So for the gravitational effects, depending on the size of the bug, we can have phase segregation, resulting in complex fluid distributions that we can see here. So basically what we can say is that depending on the fluid distribution, the communication between the bugs and the matrix will depend on the surface area that happens here. So if you have a medium phase here, that it's in direct contact with the actual matrix grid bug, we're gonna have to try to communicate both because of their spatial distribution. So we also have some bug scale effects, and this actually is a big challenge that we are currently trying to identify. So we have the small size bugs, but also we can have bugs that range to the meter scale. And one of the important things is to understand what scale is the one that actually matters. And by doing that, we will be able to simplify this complex problem, at least in a certain way, and make it more approachable by only using the ones that matter the most. Now let's talk about the complex interactions that happen. So right now in EDFM, we've done a really good job identifying the interplay between matrix blocks and the elements that made up the structure and corner point grids with any type of fracture that is represented either convex or concave. But now we have the interplay between convex, concave, 3D bugs, and also 3D Karst systems that we can see here. Here also we can see a new property that's connectivity that determines all the connections of all these systems and this intricate topology. So another challenge here is the algorithms that have to represent all the interactions between all these elements. Now let's talk about the fractured boggy carbonate reservoir model. So here I'm presenting the most important ones: the triple porosity, Stokes-Brinkman, 3D Karst, and Stokes-Darcy. The triple porosity model actually will be deemed as the most inaccurate one because of these simplifications. That's why in this case, in this talk, I'm not gonna put more emphasis on this one because we have other models that can describe free flow in a better way. So we have the Stokes-Brinkman model that I'm gonna talk a little bit more. And also the 3D Karst model that also one of the things here is that it can be used in commercial simulators, but at the expenses of accuracy. And the most accurate one that could be selected would be the Stokes-Darcy, but at the expenses of the computational efficiency. So let's talk about a little bit more about this Stokes-Darcy model. So here we have the interplay between Darcy's law in the porous region and Navier-Stokes equations in the bugs and Karst. So the important thing about this is to try to couple both of these sets of equations at the interface. And here, mass and momentum need to be balanced. And one of the works from Bieber, Joseph, and Subman was that they actually tried to come up with an equation that can couple both systems. So here, this is the initial equation that they have, basically relating the difference between the velocity in the free flow region and the tangential velocity in the porous media. And that difference is proportional to the shear rate on the flow region. And after including certain parameters as the permeability here in the porous media and this alpha parameter that is a slip factor, they were able to characterize and basically introduce an equation that can couple both systems. Other literature review present some models that model bugs as a grid bugs, as we can see here. In order to model the instantaneous gravity differentiation, they can assume these shapes and model them in that way. And also in these models, laminar flow is assumed. Now, the shortcomings about these models, definitely the potential numerical instability that it can create, because we are using an interface and the mathematical description of that is really challenging. So those problems could arise. Another one is the difficulty to keeping track this 3D interface. As we saw, they may have really complex shapes that can increase the applicability of this model. And actually, these current models out there have not been tested with dense or at least realistic fracture networks. Now let's talk about the Stokes-Brickman model. So this model tries to basically simplify the complexities of the Darcy-Stokes model. So here, what Brickman did was to come up with this equation, like let's call it the model equation. But after performing certain simplifications to the system, we can arrive to two equations actually. When you are modeling the free flow region and you take permeability to infinity, and this factor here called the effective viscosity to be the dynamic viscosity, you will arrive to Stokes equation. And on the other hand, if you try to model the porous region, if you take this effective viscosity as 0, you will arrive to the Darcy equation. So basically, this model can allow you to switch between media accordingly, and also overcomes the interface tracking problem from the Stokes-Darcy equation. About the shortcomings of this model is the two-phase flow is actually really challenging to implement, and also the three-phase flow. This effective viscosity was actually is actually a value that is a function of the dynamic viscosity, and also the porous media presents an uncertain, but is uncertain because it depends on these variables, and laboratory experiments need to be done in order to understand it and actually use it here. We also have the 3D Karst model. So here, the idea is basically borrowed from EDFM, separating the matrix and Karst in commercial simulators into two domains. The Karst system here is represented as a refined grid, and here the transmissibility between the cars follows the typical classical two-point flux approximation. Here the transmissibilities are implicitly calculated by the simulator. But the shortcomings about this model is definitely the fluid flow part, because Darcy's law is used in both domains, which is highly questionable. And also this model cannot handle fracture interactions. But here in SimTech, our main object is to develop the first commercial simulator capable of modeling free flow and Karst systems. Here we have a URSIM, our flagship reservoir simulator, and our objective is to model Karst Vugs fractures explicitly and accurately. Here our main idea is to include flow equations that can handle that complexity between free flow and Darcy flow. But in our second objective is not only to use it in our own reservoir simulator, but also to expand it to third-party simulators. So here what we're going to do is to use our ERSIM as the reference reservoir simulator and include some appropriate modifications to the third-party simulators in order to mimic efficiently the free flow. So we're confident that we are up to this challenge because we're proud to say that we developed the first commercialized non-intrusive EDFM preprocessor in the world. And these are giving us a lot of experience. And it's worth to say that all the Vugs and Karst system discretization algorithms constitute an extension of more than 10 years of development experience in reservoir simulator and also in computational geometry. And all those can be extended and can be used in structure and corner point grids. We also are not starting from scratch. We possess our own reservoir simulator, URSIM, that is readily available for us. Also, fundamental work right now is done to include the new module, free flow module, in our URSIM that can handle efficiently free flow in Vugs and Karst systems. Here we show like the general workflow that we envision. So first of all, our main object is to honor the geological studies and the geological models that the geologist team can come up. And after developing the 3D geological model, our idea is to use our EDFM approach and divide it into two phases. The first one is the discretization phase, and the second one is the flow modeling part. So here a little bit more of detail. The first phase, called discretization and representation, basically deals with the development of preprocessor that can handle fractures, Vugs, and Karst interactions. So here our idea is to separate the three domains, Vug, matrix, and fracture domains, and I came up with certain values for transport indices and interactions in order so that the flow modeling phase can take all those results and use it for the free flow module in URSIM. The main idea is to conduct at the end of the day reservoir simulations and uncertainty analysis. Here I'm going to show in a little bit more detail about every single part that basically is apart from the first phase. So the first phase talks about the discretization and representation. Here we have the first part that deals with the Vug and Karst discretization. The second part talks about the 3D interactions between all those bodies, and the final part is regarding the pore volume correction that we're gonna need to include to honor the volume of Vugs and Karst. So let's talk a little bit more in detail of every single one of them. So here, let me show you how third-party software that aims to characterize Vugs and Karst present the elements. So here we have a Vug, how it's represented, and also a special distribution of a 3D Karst system. This is how the third-party software provides the data. So as we can see here that if we try to use directly all those complexities, it may be challenging to actually use it. So in this part of the discretization, we're trying to find the best ways in order to reduce the complexity of the Vug systems, so we can actually use them in our simulations. The next step is to deal with the matrix and no-matrix interaction. So here, no matter where the Vug is located, its size or its orientation, we should be able to handle and be able to identify the connecting grid blocks that are interacting with the volume that is presented here. And after doing that, we also need to perform some volume corrections. As I show here, we developed robust algorithms that can actually calculate the volume of every single polyhedra or every single Karst system that the operator may provide. And by calculating the precise volume provided, we can accurately perform those volume corrections in the matrix grid blocks. So these are an advancement that we've done, and we've successfully been able to do this from actually data from .ts format provided. Now let's talk about the second phase that deals with the flow modeling part. So here we have Darcy and free flow modeling that is the core of our URSIM and our approach. And here we also we're gonna develop certain new transmissibility calculations and also define certain special connections that will show the interactions between the matrix and no matrix features. We also need to perform some well index corrections in the case that the well trajectory actually is intersected by a Karst or a Vug system. So here in the free flow modeling, we're performing on the fundamental work, so we can understand better the validity of Stokes-Brinkman and Stokes-Darcy equations. So after understanding and picking which is the best avenue, or maybe both of them could be similar, we'll still use, our idea is to still include both, but after our own research, we may only use one. So we are open right now to more discussion and also more understanding of all these two sets of equations and approaches. So they can be used in the free flow URSIM. And also, we are currently deriving new transport indices that can explain the communication between matrix and fractures with Vugs and Karst. those implementations will be included in URSIM as I shown here. Now let's talk about the special connections. Currently in EDFM, we have done a really good job determining the connections and the intersections between the grid blocks and any type of fracture. So we add them here as neighboring cells. And so far we have three different types of connections. But now with EDFM for Vugs and Karst, we will need to include at least 2 more that are shown here that will need also to be located in certain parts of the computational domain in the reservoir model. Another important thing I mentioned before is the fact that what happens when the flow is directly communicated by the Vug or a Karst system. This part needs to be treated differently. That's why some well-indexed calculations will be added in order to represent the higher contributions of those grid blocks. This goes hand in hand with recent work using low circulation data from drilling and all the workflows that are currently state-of-the-art with geologists. So here, let me show you how we are planning to represent oral systems. So here, as you can see, we've created this dummy model depicting all the different types of elements that we're going to work with. We have some fractures. We also have Vugs connecting with the Karst system. And one of the things about this also is that we currently have a connectivity algorithm that will be extended in order to capture connectivity between fractures, Vugs, and Karst system. So this adds a tremendous value because as we learned before from the other talks, connectivity actually plays a big role in the description of the flow behavior in the reservoir. So we will extend this current connectivity algorithm, and in that way we can better represent all those interactions happening in the reservoir. So as a summary, let me try to come up with just 3 bullet points that can summarize everything. We can say that the EDFM for fractured Vugs and Karst systems is definitely a promising reservoir simulation workflow to study and optimize carbonate reservoirs and help field development planning. An important thing about this is to recognize that those geometrical calculations and the representations of the complexity in the reservoir actually require robust spatial algorithms that can handle all those complexities. And another one is that the free flow, at least here in URSIM and in SIMTech, will be explicitly modeled and with the core of our URSIM model in order to accurately characterize and depict the fluid flow in carbonate reservoirs. So thank you so much for your attention. Now I'm open to any question.
Thank you, Joseph. See if anyone have a further question about Joseph's talk.
Yes. May I pose a question for Joseph?
Please.
Yes.
Joseph, great presentation. Thank you very much. Can you update us on where we are in terms of implementations of the different formulations? Is it an ongoing work, or are you planning to do it in the near future? Where are we now?
Sure. Thank you for that question. So currently we are working on that, and in the next talk from Mauricio, we're going to actually see a Gantt chart and that depicts all our approaches and basically a timeline. So right now we are in the derivation part. We're basically trying to in this part, in flow modeling part, we're studying in depth the Stokes-Brigman and Darcy and Stokes-Darcy model. So here, what we are doing with the help of Bruno, also we are trying to come up with the best set of equations, and at the same time trying to see what information the model may need from the preprocessor. So right now we're in that stage that we are defining the sources of information that any of these models might require. And after that, we're going to benchmark them. Maybe one will require more information, more complex information. Maybe the other ones will require less. So after that, we will decide and we will see what will be the best avenue for us to take. I don't know if I answered your question. Maybe you wanted to know more about the preprocessor also.
Yeah, if you please comment on it. I see you were able to model different geometries of Vugs.
Yes.
And Karst, and yeah, if you can comment on that, please.
Yeah. And for the preprocessor development, actually, we started that, and as you can see here, we can read all the types of information from the operator, and we started with working on the actual module that deals with the intersections between them. And also, working parallel with this is the analysis between what will be the best simplification for the complex Vugs. As we can see here, some of them might have really intricate topologies, as we can see here, really concave shapes. So maybe using the same volumes, the same bodies, will increase tremendously the challenge. So we're actually studying how to reduce the complexity of them, but at the same time preserving the actual volume. So our approach is to use those volumes, but in a more simpler way, so we can actually treat it in our algorithms.
Joseph, question. Maybe I didn't understand you very well, but when you split, you had this diagram. You split the matrix, the caves, karst, and the fractures. The scale itself, cell size, the scale, are they the same, or each element has its own scale, and then you're trying to see the volume of those? And then my second question, since I'm here, what do you do for the cell size? I mean, do you go to the smallest features that you have, like cars, for example? How do you upscale if you need to upscale?
Yeah, so that's a really good question that deals with one of the main challenges that we explained at the beginning. That is the scale. So maybe I mean, right now we're developing at least the whole algorithm that can handle all those interactions. But one of the things about this is that some isolated bugs whose scale is small enough, they may be upscale, as you said. So we have that idea of selecting, and after our connectivity analysis, we can determine that. We can determine from the data that the operator provided, we have a certain, or maybe a lot of bugs here that are actually isolated. So our idea is to use that connectivity algorithm to determine their status. And some of them can be upscaled, especially the non-connected ones, but definitely will preserve the connected ones. And can you repeat again the second question that you had?
Yeah, the second question is actually, I think you already answered my second question. Indeed. Yeah.
Sure.
Maybe here is, so here in when you showed us some example, what size of the model are we looking at, and what's the cell size?
Well, this model actually this is not just a model; it's more like a picture, but it's just to kind of show the main idea that in here in the first phase we're going to divide the different domains. So here is just represented. It doesn't have an actual scale of the model. It's just to show like a picture.
I think it's in the last one when you showed these.
Okay.
Yeah.
Maybe here.
Yeah.
You mean here, like this one?
Yes, exactly.
Yeah. So, Mauricio, do you remember the size of the grid that you helped me create?
Yeah, I believe it was 15 meters, 15 or 20 meters, the length of each grid block.
Yeah.
So we are taking into account like a reservoir scale. And just to add to the comments on the grid size, remember for the bugs, the fractures, we will use the similar approach of our EDFM, where we apply different pore volume corrections so that they adjust to the actual geological interpretation volume that was characterized. But in general, for the grid size of the grid of the simulation, in this synthetic case, we use 15 to 20 meters. I quite not remember the exact number, but it was about that for each grid block.
Hey, Joseph, can I ask a quick question here?
Sure.
I'll try and bridge the gap here from a geologist's mind to a reservoir engineer's mind as best I can. So you explained how basically you come out of, you know, a matrix system into this kind of free flow type regime. Is there any, have you guys thought about, or is there any work that's been done where you go from small scale kind of millimeter scale Vugs where flow might kind of be non-Darcian but not necessarily turbulent, and then where you're exchanging with these larger scale Karst features? Is there, have you guys considered that or worked on that kind of problem at all?
Regarding that, I think that we could. That's why we would like to have as many suggestions as we can. But in this case, our main idea is to try to simplify it in the best way. So our idea first is to, at least the small scale ones, like try to represent them if the operator provides that, like as a data, as a more geological model. And again, the idea is to examine the connectivity. Like if they actually have a connection, like in 3D space, as we can represent here, then we can definitely include them in the system. But the other ones that may be isolated, actually, they may not contribute too much, or we can actually study them further. But so far, my answer for you right now will be just to examine the connectivity. So regarding their scale.
Okay.
Can I make a
sure
on this?
Sure, Ron.
If they are small, then they may simply you know, make a non-Darcy flow. So maybe they wouldn't be represented as a EDFM block, but they would still be a matrix block where non-Darcy flow takes place using these because you know, these like Stokes-Darcy model, they are basically equations that they are averaged on the REV, representative element of volume, right? So you could still use it to describe the non-Darcy flow on the block.
Okay.